well, I would also like to thank organizers for giving me opportunity. And yeah, and also for organizing such a nice conference. And this is kind of a little bit off from my expertise, but I could learn a lot of new things, which I would never learn from the conference I usually attend. And today I would like to talk about the cosmological application of holography. And I prepared assuming the audience which are not experts of cosmology. So I guess if you are familiar with cosmology, probably it's a little bit boring, but yeah. And the question from non-experts are pretty much welcoming. So there was a nice review by Yasusada Nambu in about a bit of inflation and cosmology. So apart from the very beginning of the history of the universe, we more or less know the standard history of the universe. But we don't know yet how it has started. And especially that the observational, a lot of the observations suggest that there was an accelerated epoch called cosmic inflation. And cosmic inflation is we don't know the detail, but the overall structure will be like the energy density has the vacuum energy of the scalar field or some field had led to the rapid expansion of the universe, and which can be seen from the Hamiltonian constraint by inserting a constant in the right-hand side, which gives you exponential expansion. And since we know how the universe evolves later on, more or less, so because of that, by observing the cosmic microwave or the galaxy distribution, we can capture the kind of fossil encoded in such a cosmological map of the universe. And the interesting aspect of cosmic inflation is the typical energy scale of inflation could be almost the God scale. And the latest observation suggests that the Hubble parameter, or more or less energy scale of inflation, could be as high as like 10 to 14 GeV. So in that sense, since it is much higher than any ground-based experiments of high energy physics, the energy scale accessed by any accelerators. So because of that, it's a natural laboratory to experiment HEP physics HEP. And for instance, so here is Einstein equation, but in UV, the gravity has to be modified to be complete. And one of the promising candidates is string theory, and the low energy effective field theory of string theory predicts the bunch of radiative corrections, and UV completion might be achieved from completely different way. For instance, breaking a Lorentz symmetry, as was suggested by Fujaba. So this is a modification of the left-hand side, and also for right-hand side, at least inflation requires beyond standard model physics. And also that apart from the driving force of inflation is called inflaton, and apart from inflaton, there might be other fields called spectator field, and such fields may have various spins and various mass spectrums. And those things may be able to be accessed by cosmological observations. And in the history of the universe, we can see a lot of correlators, like the CMB, and we can see the 2-point function or 3-point function correlators, and also the galaxy distribution, and also the galaxy shape measurement. And we see a lot of correlators, which is those things are called cosmological correlators. And since the initial condition of such a structure formation was encoded at a reheating surface, which is basically the end of inflation, and by tracing back the history of the universe towards reheating surface, basically we can capture the information of about how the inflation was driven, or what was the physics at that time. Yes, so we don't know that who has driven such rapid expansion, but geometry of inflation is probably we already know, and which is well approximated by the zeta symmetry. And let me briefly review what is the zeta spacetime. And the zeta spacetime and anti-zeta and also Euclidean ADS have basically a mathematically similar structure. And all of them can be described as D+1 dimensional hyperbolic, the zeta and Euclidean ADS are both embedded D+1 dimensional hyperboloid in D+1 dimensional, D+1, 1 flat spacetime in this metric. And just the signature is a little bit different. And this panel shows the geometry of Euclidean ADS and the zeta. And the black line corresponds to the null line. And as you go away from the center, in the case with Euclidean ADS, it approaches to the null, which is conformal boundary. And similarly, the zeta also approaches to the null line. We just have to rotate 90 degrees. And those two geometries are connected by analytic continuation. So because of that, we naively expect that we can learn things about the zeta from Euclidean ADS. So Euclidean ADS is in that sense sort of the bridge which connects physics in DS and physics in ADS. Oh. So in cosmological, for cosmological correlators, what we consider is not like a scattering amplitude. It's not in-out, it's not the in-out stuff. And instead, we need to calculate the expectation value. So because of that, we have to consider a closed time path, which it's sandwiched by the same quantum state. And if you put the 2 points and along this closed time path, and then take the contraction, they appear as 4 different types of propagators, which is Feynman, Dyson, and the Weinmann and the conjugate of it, unlike the case of in-out. And this is one thing I'd like to emphasize for cosmological correlators. And another thing is in the case with inflation or the zeta, so, we often use a vacuum called a Bunch-Davis vacuum, and which is defined by requiring the regularity at so those two edges as past infinity. So by rotating towards the imaginary direction and by requiring the regularity there, it uniquely determines the vacuum state to Bunch-Davis vacuum or Euclidean vacuum or adiabatic vacuum, which have various different names. And free level, this propagator corresponds to the vacuum vacuum, which is determined by simply by the zeta invariance and also Hadamard condition, as was argued by Bruce Allen on 1985. Yeah, so this, as you may see from this initial condition on Euclidean vacuum, this basically picks up sort of the ground state of the system. And as I mentioned already, anti-zeta or Euclidean ADS or zeta have a mathematically similar structure. And here I'm writing for the ADS and DS. And in the case with ADS, it is SO2,3, but well, this is just because of the signature difference. But in the case with the DS, it corresponds to SO1,4. And in one carry patch, the ADS is given by this way, like so. So is given by this way. And on the other hand, dosita is given by the similar metric.
Excuse me.
And yeah.
Yeah. Are you using any pointer or pen? I cannot see it.
Really?
Of course, your slide. I can see your slide, but I cannot see any pointer or yes. There appear some palette, but
this can be seen.
No, I can see nothing.
So if I write something, do you see?
Yeah. I can see it. Yeah. Yes.
Okay. Yeah, so
okay.
Yeah, this is just to say that the ADS and DS are mathematically similar. And in the case with ADS, the boundary is at here. Do you see this? Boundary is at here in the left edge, but since we need to analytically continue to go to zeta, so because of that, the boundary in the zeta is here. And those two geometries are connected by this analytic continuation. Oh, I see. Okay. So yeah, so based on this mathematical similarity, DS-CFT conjecture was proposed by Strominger Witten in 2001. And but physically, the situation in DS and ADS are different. And first of all, the holographic direction here becomes time-like. So because of that, the CFT, the boundary CFT lives on spatial boundary, unlike ADS, where the boundary is just like that space. And also, dual CFT is, in the case with DS, non-unitary, which can be seen just by analyzing, say, a free scalar field, whose scaling dimension is given by, in the case with ADS, it is given by the upper formula. And on the other hand, in the case with DS, it is given by this lower one, this guy. So as you see that inside of the square root can be negative for the heavy mass limit. And this basically one of the consequences we can see the non-unitarity of the zeta. And related to this, lately there was an interesting paper by Isono, Liu, and Nomi. And they pointed out that the principal series in Rosetta, where the inside of this square root becomes negative, has similar properties with the situation below BF bound in ADS, whereas we also see the non-unitarity. And also in the case with ADS, we are seriously lacking the concrete example. Yet by Aninos and Hartmann and Strominger has proposed one example where we can, smoothly do the analytic continuation. And also by Tetsuya talked about the entropy in zeta, yet still the relation with area rho is not very clear in the case with zeta, in the sense that we don't know what's the relation with a microstate and so on, as much as we do in ADS. However, we can still find the necessary building block to see to expect the duality also in ADS, and actually we can consistently calculate the correlators. Let me see that. And so first, let me talk about computing the boundary correlators from bulk physics. And here, let's let's assume that by using the equation motion for 4-dimensional bulk equation motion, we can likewise the Hamilton-Jacobi, and getting rid of one derivative, we can express the action in terms of the variables in boundaries. And imposing one trivial boundary condition in one side, we can write down the action in terms of the fields on the other boundary. And taking the derivative with respect to the phi hat, which lives on on the other boundary, here I took Z1. And then we can obtain the 2-point function. And in the case with Euclidean ADS, it is given by the like this. And similarly, also we can also calculate the 2-point function of the boundary operators like this. And because of the analytic continuation, it has a negative sign. And we can also calculate the bulk cosmological quantities from boundary operators by identifying the wave function of the universe with the generating function given by this way. And since this is the wave function, the probability, this is a probability distribution, and probability distribution is given by the square of the wave function. And yeah, so because of by using this probability distribution, the bulk correlators, which gives the fluctuation of scalar fields, can be calculated in this way by multiplying the probability distribution. And then, for instance, taking the second derivative with respect to phi, we can obtain the 2-point function of the boundary operator. On the other hand, in the viewpoint of these bulk correlators, taking the second derivative gives you the inverse of the dispersion. By equating those two expressions, we can calculate the bulk, the scalar field in terms of the boundary operators. Since it is the square of the wave function, it is given by the real part of 2-point function boundary. And here, let me consider a massless scalar field, which should correspond to the scaling dimension of 3, since I'm considering a 1+3 dimension. For general dimension, I just have to replace this as D. And by doing a Fourier transformation, this gives you 6 minus delta, which gives you 3. And then putting this expression, using those two expressions, we obtain the bulk 2-point function is given by 1/k to the third, which basically gives the Harrison-Zeldovich spectrum, which is a 0th order approximation of the CMB spectrum. And this is probably the most friendly way to derive this Harrison-Zeldovich spectrum to people who are familiar with CFT. And actually, observation tells you a deviation from scalar invariant spectrum. So precise, it is not, it should be still a bit of deviation from 1/k to the third, but this can be explained by taking into account from the deviation from the zeta. And yeah, so this was taken into account by considering, by introducing deformation from conformal field theory. Here is, so far it has been an overview of DS CFT up until almost 10 years ago. And I could have gone through those, the application to inflation, but perhaps it was a bit too much detail for people who are not working in cosmology. So because of that, instead of that, I would like to do a review of recent progress about, this is not exactly to zeta CFT, but it's kind of the application of the technique which has been developed in ADS CFT or boundary CFT. Before changing the topics, is there any question up until now? Okay, if not, let me go on. So, which is called Cosmological Bootstrap.
Ugaji-san, please.
Yeah, I have
There
a
is a
question.
question.
Okay, is there any generalization of this DSCFT to include the black hole in the space-time?
Not that I know.
Okay, yeah, I also don't know. Thank you.
Yeah, thank you for the question. And let me talk about the cosmological bootstrap. So conformal bootstrap gives you a relation between the S channel and T channel, so swapping the contraction, which follows from the theoretical consistency of the conformal field theory. And likewise, the goal of the cosmological bootstrap is the following. So imposing the zeta symmetry and also imposing the correct UV energy singularities. And also there is a bit more assumptions, but based on those two assumptions, write down, so the goal of this program is to extensively study possible exchange diagrams. Likewise, conformal bootstrap to bootstrapping from the singularity structures. And this program is pretty much based on or inspired by scattering amplitude, the progress in scattering amplitude. So if you were to calculate Feynman diagrams for a given Lagrangian, is there any question? Okay. So yeah, so if you were to calculate the Feynman diagram for a given Lagrangian, then you would find a lot of redundancies. And then at the end of the day, when you want to calculate the scattering amplitude, a lot of the terms end up with just zero, which is kind of waste of time. And scattering amplitude program is to get around such the unnecessary steps, and also to get around the redundancies in Lagrangian, and also bootstrapping scattering amplitude from the physical principles like unitarity, causality, or locality. And in the scattering amplitude program, we consider contracted amplitude by projecting into helicity variables, the tensorial, projecting the tensorial amplitude to the by contracting with helicity variables. And this is basically just a reshuffling of the different terms. But you can see how powerful is it, for instance, by looking at this famous Parquet-Taylor formula. So when you just calculate the gluon scattering amplitude of maximally helicity vibrating one, and then you would find more than 200 diagrams. But by using this, this language based on spinel representation, which can be simply summarized with this compact expression. And yeah, so this cosmological bootstrap program is to do something similar also for the cosmological correlators, and also bootstrapping the UV singular structures. And the question is, how can we connect the cosmological correlators with UV singularities? And for that, Madsen and Pimentel has pointed out some interesting properties, which is, so let me consider this 4-point function. This 4-point function, which can be schematically given by this way. So this KT is a summation of the 4 momenta, K2, K3, K4. So since this is a cosmological correlators, this is a spatial Fourier mode. And interesting thing is if you take the limit where the summation of all 4 momentum goes to 0, then this cosmological 4-point function is roughly given by this structure, where which is like the amplitude is determined by the scattering amplitude in the flat space times some pole structures of KT goes to 0. So one can understand the reason why we get this formula as follows. So in the cosmological correlator, there is sort of a UV infrared duality in the sense that when you consider the small momentum limit, that corresponds to the deep UV in the sense that we are looking at the deep, the past infinity, whereas the geometry goes closer and closer to the flat space. So because of that, when you send the momentum, total momentum to 0, then we are kind of seeing the flat space. Or in other ways, in the case with zeta, there is no energy conservation, but by sending KT goes to 0, by setting KT to 0, we are kind of enforcing the energy conservation being consistent with the situation of flat space. So this is kind of the physical explanation of the reason why we get the flat space amplitude by taking the total KT goes to 0. And so this is but still it's not very clear how to connect the exchange diagram with UV physics. And which is supplied by this Watakahashi identity of spatial conformal transformation. And I haven't said probably clearly, but here I'm focusing on the future infinity of the zeta, where the QFT, which lives on this future infinity, satisfies the spatial translation symmetry and rotation symmetry, and also dilatation symmetry and spatial conformal transformation symmetry. So we have word identities for that. And the dilatation, WT identity for dilatation can be simply satisfied by multiplying a proper factor. And the non-trivial one, which comes from SCT, and which can be schematically, after a little bit of massage, we can write down this Watakahashi identity in this way, which are schematically. So this is like the delta U is some derivative operators, and which operates on this exchange diagram. And that gives you this contact diagram, for which when you send KT goes to 0, it simply gives the amplitude is characterized by the scattering amplitude in the flat space. And this is kind of analogous to the situation in the flat space. So in the case with the flat space, by multiplying S minus M squared, which corresponds to the singular structure of the exchanged particles, you can get the contact diagram. But you get some similar formula from the Watakahashi identity of SCT. And as I mentioned, this right-hand side can be, we can know how it behaves in the limit KT goes to 0 from the scattering amplitude in the flat space. So by solving this derivative equation, we can calculate the exchange diagram in the zeta which is compatible with the physics in flat space. Yeah, so this is a result, and this is an expression of delta U. So in the case with the 4-point function of CFD, in position space, it is characterized by the two cross ratios. And since here I'm taking a momentum space representation, we don't have a cross ratio, but still it is characterized by the two variables, which is U and V. And this Watakashi identity is it's a second derivative equation with respect to U. And we get a similar expression also for V. This operation naively changes the diagram in this way, like reshaping the exchange diagram. I'm just changing the way to write to show the corresponding momentums. And what is interesting is when the internal momentum is small, this corresponds in the position space. This corresponds to the configuration like this, like the two pairs of the points are separated largely, and in this limit can be understood by the OPE. And so in that sense, we know well about this limit. And okay, in order to solve this second derivative equation, we need to determine the boundary conditions, and one boundary condition comes from this one. And the other one can be determined by imposing the Bunch-Davis vacuum, because Bunch-Davis vacuum is sort of the least singular vacuum, which does not have singular pole, which appears in other types of vacuum. So by imposing those two boundary conditions, we can solve this second derivative operation equations with respect to U. And this is a result. And yeah, so the left part shows a particle production. And on the other hand, the right part, which corresponds to this right diagram, is sort of the EFT limit. This by solving this Watakashi identity, we can reproduce, we can connect those two limits. Another similar approach, which is also pretty much kind of inspired by ADS-CFT, is a Marina space approach. And maybe familiar with that, but Marina transformation has various advantages to analyze conformal field theory in a flat space. So when you are just considering like a gap theory, then the momentum representation is quite has advantages to encode unitarity or causality or those kind of physical properties, as was nicely explained by Toshifumi Nomi. On the other hand, this momentum representation is not very, it's not very good representation to address CFT. For instance, which can be seen by considering the 2-point function. The 2-point function in CFT is given by the power of form, and which can be Fourier transformed in this way. And as you see, so since there is a branch cut at the origin, so it is not, it's kind of problematic to impose those physical properties. And Marina transformation gives a prescription which makes it easy to implement those properties. And yeah, so this is a definition of the Marina transformation. And for instance, let me choose F Tudor. So this one is, so sorry, it has jumped to somewhere. Okay. So yeah, so let's say that F Tudor is given by 1/s minus delta. And then taking residue, one can get, let's say that we consider x which is larger than 1. And then taking closing the contour with the right side, we can get that the f of x is given by 1 over x2 delta, which is basically the form which we wanted to evaluate. So by using the Marina transformation, we can express the 2-point function or the correlators in CFT, making the pole structure clear. So in that sense, when I borrow the word from ICTP lecture by Go Pacman, so Marina transformation is basically to pick up different scaling behaviors for power law decomposition. And compared to the situation in ADS, we don't know much about, the zeta QFT. And in the case with ADS, we know that we have the well-defined notion of unitarity, and we know that we have non-perturbative understanding of singularities, but we are kind of pretty much primitive about zeta. So the idea which was suggested by Slate and Tarona is the following. So this is to give a clear mapping between the situation in ADS to DS. So the obtained formula is basically you can calculate just by directly considering QFT into zeta, but the hope is making the relation between the situation in zeta and ADS, and we can borrow the knowledge which is obtained in ADS. And so as I already mentioned, DS and Euclidean ADS is related with analytic continuation of this one. So eta is conformal time of the zeta, and z is a holographic coordinate. And maybe I'm not doing well with time. Okay, maybe I can skip some part. So for instance, in the case with a harmonic function in ADS, using the split representation, we can express it by integrating over the conformal boundary, like this. And then taking Fourier transformation, this harmonic function can be given by this way. And we can find that by doing analytic continuation, which connects between the DS and Euclidean ADS, which can actually obtain the corresponding expression of a boundary propagator of DS, which can be directly also obtained by doing computation in DS. And also, it is known that this back boundary propagator in ADS can be how to express in a Marine MB representation. And this can be also mapped into DS language just by this analytic continuation. And for instance, by using this language, the 2-point function, 2-point propagator of DS can be given by this way. This is a typical form of Marina transformation. So this contains the integral along the imaginary axis, making the pole structure, which is expressed by the gamma function. And this is actually obtained by just the simple analytic continuation from Euclidean ADS. And similarly, we can also obtain bulk propagator. So all kinds of the bulk propagator, like Feynman and Dyson and so on, by using the conformal partial waves in ADS. And since we already have bulk boundary propagator and bulk propagator, we can calculate for instance, the 4-point function into zeta like this by making the relation with ADS clear, and also that making the pole structure clear. And another thing is about exchange diagram. And what is interesting is this in the paper by Slate and Tarona, it has been pointed out that the exchange diagram in zeta can be given by the linear combination of the exchange diagram in ADS with delta plus and delta minus. So yeah, so this the left-hand side, as I've been emphasizing, the left-hand side can be obtained just by direct computation in to zeta. But yeah, so the hope is to use the knowledge of ADS as a guide to understand DS. Yeah.
So the one of the reason why people, introduce this Merlin variable for the case of CFT is that this is the analog of this Mandelstam variable for the CFT. In the case of DS CFT, there is any physical interpretation of this variable S?
Yeah, I think similarly to this previous approach, by we can also bootstrap the singular structure also in DS.
Yeah.
So yeah, it's kind of the relation is kind of quite clear also in DS. The relation between the situation in DS and ADS.
Yeah. Okay.
So actually, the exchange diagram itself is just a linear combination of it.
Okay.
Ishibashi-san, please go ahead.
So you just consider some of the correspondence between the DS and ADS, but ADS in the globally ADS has a single infinity, conformal infinity, and
here I'm just considering a Poincare patch.
Poincare patch. So
yeah.
In the ADS.
Okay.
So sorry. Poincare patch in ADS, you mean?
DS.
DS.
Yeah.
So
yeah. So
just a
corresponding ADS is also
one of the
patch.
Okay, so then your correspondence between the infinity of the Lorentzian Dozita and Euclidean ADS. Is that correct? Or Lorentzian Dozita space and Lorentzian ADS?
Lorentzian Dozita and Euclidean ADS.
Oh, Lorentzian Dozita and Euclidean ADS.
Yeah.
And in the Euclidean ADS has a single boundary. And that, right? Euclidean ADS and Lorentzian Dozita with Poincare patch. Is that correct? So the only you consider just a single conformal infinity in DS.
Right.
I see. Okay.
So yeah, so just considering this.
I see.
Yeah.
Okay.
So maybe I abuse the word, but maybe saying corresponding is not the right word. This is just analytic continuation.
Okay. Thank you.
Since I think I'm not doing well with time, so how much time do I have?
15 minutes, including
okay.
question time. Yeah. So.
Yeah, I'm gonna change the topics a little bit. So, are there any questions so far? Okay, if not, let me go on. Maybe I will finish with talking about the detectability of spinning particles. So, as I mentioned, by using this technique, we can calculate this one. So the consequence of the particle production encoded in the 4-point function. So the question is, can we observe it? So if it is possible, which means that we can see the imprint of the very massive particles, which were generated by using the high energy of inflation. through the cosmological observations. So in a way, so far we have talked about the accelerators, accelerating, but cosmological observation supplies a role of CMS or ATLAS, like detectors. And yeah, so this is the exchange diagrams, which I have talked so far. And I didn't mention explicitly, but by using the weight shifting operators, we can change the spin. Yeah, and maybe I could have mentioned that I explained about the two different approaches to calculate the exchange diagram. One difference is in this Marina space approach, the external scalar field can be general. So delta can be general, while the cosmological bootstrap approach still has a restriction on the external scalar field in the sense that it has to be discrete, it has to be connected with the conformal scalar field with a weight shifting operator. So the possible scalar field is kind of discrete, but that restriction does not exist for this Marina boundless representation approach. And yeah, so this is just to say that, you know, this internal exchange particles can have, you know, various spins. This information of the spin is encoded by momentum dependence. And yeah, so in order to consider a 3-point function whose observation is easier than the 4-point functions, let me send one of the 4 legs to 0, momentum of the one of the 4 legs to 0. So then that is replaced by the background value of the scalar field. And then, yeah, so, but still we can recycle the result of the exchange diagram. And according to that, through the you know, the momentum dependence of the interaction vertex, this 3-point function has a very, you know, like characteristic momentum dependence in the limit where K3, the one of the leg, is a momentum of the one of the leg is much smaller than the rest of 2. Actually, this configuration is the easiest to observe. And in this limit, this 3-point function is proportional to the power of S. S is the spin of the inner product between larger K or the shorter wavelengths and the smaller K3, as was first derived by Arcani-Hamedo and Maldacena in 2015. And yeah, the question is, can we observe it? And before that, let me talk about the characteristic amplitude of this 3-point functions. Let me focus here on principal series, and which is given by this scaling dimension delta. And the amplitude is also proportional to Boltzmann factor. And the temperature here is given by basically h divided by 2 pi. And also, since there are 2 interaction terms, it is proportional to the interaction between the spinning particle and the scalar field, which is basically inflaton. And since we have replaced one of the 4 momentum with a background field, it is also proportional to phi dot. And this information of the vertex is encoded by this encoded as a momentum directional dependence. And this is just a power spectrum of the 2 different momentum. And the interesting thing is, as you know, consequence of the resonant production of the massive particles, it has sort of the oscillatory behavior. But as you see, this is since it is suppressed by the Boltzmann factor, unless luckily the mass of the particle is around of order Hubble, it is exponentially suppressed. And also there is also so this basically this K over K1 over K3 to 3/2 is basically the dilution factor between the two horizon crossing moment of the short mode and long mode. Since the massive, basically massive fields are diluted in a super horizon evolution or just a large scale evolution, because of that, it is diluted. And also that, in the case with inflation, it's typically weakly coupled. And if you want to enhance the coupling, considering large coupling, it was shown by one in this paper that when you enhance the coupling between the spinning particle and inflatons, and basically as a radiative correction to the mass of the spinning particles, it makes the Boltzmann suppression more severe. And there is several ways to evade those suppressions, which is to consider spinning particles with a light mass. But that is not possible for as long as we consider this symmetric situation, well, like a zeta symmetry. But by considering the explicit breaking of the zeta symmetry, or considering the global rotation and violation of the global rotation symmetry, this Higuchi bound, which gives the lower bound of the mass, can be avoided by allowing us to consider light spinning particles. But in the minimum extension from the zeta, please remember that those amplitude have to be suppressed by those three factors. Let me finish my talk just talking about the situation of the observation. So far there has been three different observations. One is observing the 3-point function of CMB. And the second is observing the 3-point function of the galaxy number count. And you count the number of the galaxies in each area and take statistics of these correlators. And also the information of the spin is also encoded in the shape of the galaxies. And here, let me, since, the CMB has been so far the most, has given the tightest, or the most accurate observation or detection of this, or the tightest upper bound on this kind of signal. But, let me also emphasize that the next decade is sort of the era of the large-scale structure surveys. Those surveys will tell us about the wide and deep, the skies, and especially Euclid and LSST and Roman Space Telescope, the imaging surveys, which are going to observe the shapes of the galaxies in increased precision. So it would be nice to discuss about the potential of those imaging galaxy surveys. And this is actually more or less the end of my talk. And so this is one of my collaboration with Kazuhiro Kogai and Akitsu and Fabian Schmidt. So the punchline is the following. So as I mentioned, when the spinless particle was exchanged in during inflation, the 3-point function is proportional to the here I have written more accurate expression, which is a Legendre function, but basically the power of the inner product of the long mode and short mode to the S. S is here spin. So this characteristic angular dependence is encoded in the statistical property of the shape of the galaxy.
It seems
our universe from different spins. So what we found is, let's consider elliptic galaxies, and then the galaxy shape
connection has some problem.
can be decomposed into. Can you hear me?
Yes,
Now,
but the internet seems to be rather unstable.
Sorry, was that all the time like that?
just 1 minute before also, I think this Huey. I think, yeah, all from this transparency. I just
Okay. Can
again stopped.
Stop.
Urakawa-san, could you turn on microphone? And
yeah. So okay. So
okay.
General. iPad. What happened?
Urakawa-san, could you turn on microphone? I know. Just
can you hear me?
Yes.
Now can you hear me?
Yes, I can hear you.
yes.
Sorry.
Okay.
Do you see the screen?
Yes, I can see it.
Yeah, okay.
Yeah,
Let
yeah.
me just finish with this. Yeah, so I was saying that the 3-point function generated by the exchange of the spinous particle is proportional to the power of inner product of the long mode and short mode to the s is spin. Can you hear me?
Yes.
Can you?
Yeah. Yes, we can. Yeah.
Okay, sorry. So yeah, so the question is how we can detect such angular dependent 3-point function. And yeah, so here we are considering the observation of the galaxy shapes and take the statistics of it. And we can decompose the shape, deformation of the shape of the galaxy using the orthogonal basis, which is a spin harmonic functions. And which has, since they are orthogonal basis, we can decompose them. And the interesting thing is a different spin, the signal of different spins are encoded in different, the deformation shapes. For instance, spin 2 deformation, this is a spin of the deformation, the right side. For the spin 2 deformation of the galaxy shape, for that, is it only comes from the 3-point function, which is generated from the spin 2 particle. And likewise, the spin 4 deformation of the galaxy shape can be generated only from the 3-point function, 3-point function generated by the spin 4 particle. And similarly, the spin S deformation of the galaxy shape can be only generated from the exchange of the spin S particle. So in that sense, we can kind of separately pick up the information of the different spins, which are excited during inflation. And we also did the forecast considering like a LSST type observation, which allows us to consider a massless, sort of massless spin for particles of the amplitude of order 10. Which is still large compared to the when we consider the suppression which was described in the previous slide, and also to consider massless, as I said, we need to break the zeta symmetry explicitly or global rotation symmetry. On the other hand, the massive particle, which is kind of the simple extension of, which is possible with a simple extension of the S. And it's almost impossible because the amplitude has to be almost 10 to 5, which basically is a limit to make the perturbative expansion possible. But that's the situation. And also the CMB and 3-point function of galaxy number counts are kind of similar, and the order is more or less similar. And that's the situation. Yeah, so I think I stop here. And actually, since I skipped some parts, the summary slide is not particularly about, it's not reflecting what I have talked, but here in this talk, I have explained about the situation of the highly symmetric case, but it's still, in the case with, such a zeta symmetry, we can connect the, can you hear me?
Yes.
Oh, okay. I thought I was still talking on my own. Yeah, so in this zeta case, the good thing is we can kind of borrow the knowledge of ADS or the QFT in a flat space, and through the Bootstrap program initiated by Alkani Hamedo and Barman et al., we can connect the inflationary correlators with UV physics. And also through the many space approach developed by Slate and Tarona, so the relation between the situation of Euclidean ADS and DS has kind of become quite clear. I leave this here. Thank you. I'm sorry for this disturbance.
Thank you very much for great talk. So now it's in some break time, but we can accept some questions, still accept some questions. Is there any question or comment? Okay. Okay, Shiromizu-san, please go ahead.
What means by shape of galaxy? So you say that shape of galaxy constrain the spin. So,
Mhm.
but usually the galaxy forget about the initial condition of.
Sorry, galaxy what?
So yeah. So what means by galaxy shape? Usually,
So,
galaxy forget about the initial condition of the cosmological perturbation. The galaxy
right.
itself.
So, right. The definition of the galaxy shape is given by considering the moment and integrating about, let's say that in two-dimensional space. Okay, let's consider three-dimensional space and integrating over x1, xi, xj, x3 with the weight of the density. And this spin is and the reason why the galaxy shape trace the initial condition of the cosmological fluctuation is because of the tidal force. So which I didn't explain. So the tidal force is basically the position dependence of the gravitational force. And with basically tidal force distorts the shape of the galaxy, right? And skipping the detail, and if there is a 3-point function, which is generated by the spinless particle, and that generates deformation of the galaxy, so deformation from sphere, let's say. So in the imaging survey, we can just see the 2D image, which is integrated along the line of sight. So let's say that without deformation, it has to be sphere. And in the usual cosmic sphere, we are seeing just like elliptic deformation, which corresponds to the spin 2 deformation. But we can consider that in principle, we can observe more complicated deformation, like this blue line and red line. And the claim, what we found is, okay, and using the spin spherical harmonic function, we can decompose the deformation pattern of the galaxy into orthogonal basis. And what we found is the imprint of the spinless particle is encoded only in the spin S deformation of the galaxy shape. So the deformation from sphere, let's say. But this is a situation only in the large scale. So let's say that I think it was like, yeah, I don't remember the detailed number, but order 0.1 megaparsec, I think. So below that, it's all the the consequence of all the spinning particles are mixed up because through the nonlinear effect. But as long as we consider the large scale, the imprint of the different spin particles appear only separately by observing the different types of deformation. Was it clear?
Yeah, thank you.
Okay.
Thank you.
So time is already up. So is there any urgent question? So if not, let's thank speaker again. Yeah.
Sorry for the bad connection and this inconvenience.
Hey, it may be okay. Yeah. So the next talk will start 11:15 p.m. in Japan time. So we have about 5 minutes break. So Urakawa-san, could you stop your sharing?
Sure. Did I?
Okay. Hello.